Awesome. I'd love to see Mike here.
Yeah.
I'm not sure if Vitalik and Carl are going to join. They're out on a walk on the beach right now.
Nice.
I decided to kind of opt out of that, but if they come back, I guess they might join.
Okay.
We're all in kind of Singapore doing some kind of research on about a bunch of Casper stuff. Today we spent time. I mean, I guess if you don't mind, I can jump into it.
Please go for it.
Today we spent time working on calculating penalties for Casper the Friendly Finality gadget, which is kind of like this really simple consensus protocol addition to a blockchain that Vitalik has come up with, which basically is like probably the simplest consensus protocol I've ever seen in some sense. And we're kind of working on the incentivization mechanism design kind of questions.
Awesome.
Wait, Danny, can you mute your mic or mute your computer?
Yes.
Sorry.
Yeah.
So basically the story is kind of as follows. Whenever there's a safety violation, which is to say 2 finalized blocks, then there's a whole bunch of Byzantine faults due to equivocation that can be identified objectively. However, on the other hand, with liveness faults, we don't have perfect attribution because it's not clear if people are missing because they're being censored or because they're offline. And so basically, we are looking at some of the different considerations about how to penalize them for that fault, even though we can't perfectly attribute it. So basically, we have a couple of cool results. And assumptions. So one of the results is that firstly, we need some kind of notation to talk about who might be faulty, and what we've kind of come up with is basically a disjunction of like conjunctions, which are basically say which basically list all of the coalitions who might have caused the fault.
Okay.
So basically, we have like a list of coalitions, any one of which could have caused the fault, and this is like a complete list, and basically is kind of like the limit of the attribution that we can do. And basically, we have the following kind of result: if every coalition gets paid the same amount. Gets penalized, and penalties and rewards are kind of there's you can kind of do this transformation between them as far as like the game theory is concerned. So if you penalize every coalition the same amount, meaning the sum of the penalties assigned to the members of the coalition are the same, then that's a local minimum for griefing bounds. So if you were to say punish one of the coalitions that might have done it less or more than any of the others, then that would lead to more griefing opportunities. Griefing, by the way, is when you can like do something at your expense in order to make someone else lose money. And this kind of is inherently a problem whenever faults are not attributable, because it might have been like coalition 1 that did it, but there's like members in coalition 2 which aren't in coalition 1 that are going to have to be penalized because the protocol can't tell if it was coalition 1 or coalition 2 that did it. And so basically,
so just how does this work? Coalitions overlap?
It works just fine. So I mean, the result is that the coalition on net needs to be penalized the same as every other coalition on net, and basically the sums of the individual penalties need to kind of satisfy this to have this griefing bound, and basically,
so an individual that's participating that is a member of multiple coalitions is paid the max or the sum, or I'm not following.
So that actually is something that where we're still kind of debating somewhat, because but my favorite kind of my favorite kind of approach is basically to say that if you are part of more coalitions, then you are more guilty, and you should be penalized more. And I think that people more or less are in agreement with this, but only within bounds, namely within the bound that I just gave earlier, which is that every culpable coalition needs to pay the same amount in total. So you can imagine an example where there's 4 coalitions, 3 of which A appears, one of which 2 other, like let's say the first coalition is AB, the second one is AC, the next one is AD, and then the third one is EF. All of these coalitions have to penalize the same amount because we don't know who did it, and if we penalize them differently, then we would increase the griefing bound. And but like the combinatorial thing basically says that, like, you could punish A more than you punish B or C or D, because like A appears 3 times, whereas like B, C, and D each appeared once. On the other hand, E and F each only appeared once, but in order to bound griefing, we kind of need to penalize them both with a total of this like kind of coalition penalty.
And what certainty do you have on membership in a coalition?
Well, basically, this is kind of like an exhaustive combinatorial kind of approach. So, for example, imagine if we're waiting for 2/3 commits, and we only receive some number less than 2/3, and call that number like set P. Then any coalition that hasn't any set of nodes whose members haven't given commitments, whose weight is more than 2/3 minus P, is suspect, because they could have been the coalition that prevented the commitment from happening. And so basically, like, we can kind of like exhaustively list all of these possible coalitions.
Okay, so that's a 2 to the n minus 2/3 size.
Yeah. It is. But
that's the bound above 500.
Yeah. But the kind of approach here is to like, kind of play out all of the kind of logic of the incentives. And then when we go to implementation, we're going to find that there's a bunch of simplifications.
Okay.
But like the kind of idea is that it would be really cool to figure out how to incentivize kind of in this more abstract game where basically we just have like some set of coalitions, each of which could have caused it, but we don't know who. Like, incentivization is relatively easy when faults are attributable and when good behavior is attributable, but it's kind of trickier when it's like not, right?
Sure.
And so basically what we kind of want is to be able to, or what at least I kind of want, is to be able to say what the payout should be for every member of like this like validator set, just given this like list of coalitions who might have been culpable. And there's basically 2 kinds of considerations that we're looking at right now. One of them is fairness, and the other is this whole bounded griefing factor thing. And the minimizing the griefing factor means either not punishing everyone, or punishing not punishing anyone, or punishing all the coalitions with the same amount. And then from that, we basically have some degree of freedom as to who gets punished how much, because basically there's many possible penalties that add up to this constant for every coalition. And my kind of my intuition here is that if you appear in more coalitions, then you should be penalized more. Basically, because let's say, like, no matter what the probabilities are, you are more likely to be guilty if you end up in more coalitions.
Is there a way of having multiple people team up on someone else to make it appear as though they're in multiple coalitions?
You took the thought right out of my head.
So I mean, the whole this list kind of gives you exactly that information. It says, like E and F could have done this, and that makes it look like A and B might be faulty, or A and C might be faulty, or A and D might be faulty. So we can basically infer from the protocol state the set of all possible suspect coalitions, and from the set of all possible suspect coalitions, we get to see exactly who could make who look guilty. And from knowing the total penalties on every coalition, we can basically say what the griefing bound is, because griefing basically is when one coalition spends some amount of money in order to make someone else lose money.
What defines a node or group of nodes as being in a coalition? I'm sorry, I missed.
So every set of nodes is a coalition. Basically, there's like kind of players in like game theory, or like these individual actors. Coalitions in game theory are like sets of players, and basically, the presumption is kind of that this set of nodes might be kind of colluding to lead to this result. There's kind of like one of the kind of things that we want for this mechanism sign question is for the equilibrium to be for the grand coalition to work towards preserving protocol guarantees. And the grand coalition is a coalition of every node. And what we really don't want, or we're really trying to disincentivize, is for like some sub coalition to say undermine protocol guarantees and for that to be profitable for them. Mm-hmm. And basically every protocol guarantee, basically whenever it's violated, there's like some evidence left behind of like who did it, and that evidence is sometimes perfect in the case of like in the case of safety violations with perfectly attributable faults, like we're kind of really accustomed to having now. And then the liveness faults, on the other hand, are much less attributable, because, for example, if A was expected to send a message to B and it didn't happen, it's not clear who is at fault. If some node is offline, it's not clear that they weren't censored. And so the question of who is culpable when there's a liveness failure leads to basically this kind of like list of possible suspects. Right. And basically from this list is the idea is that we should be able to derive the penalties. And so basically most of the work that we've been working on is kind of like this story for, kind of in abstract and for Vitalik's finality gadget. So anyways, I feel like I've gone a little long. I'm happy to pass the mic.
Cool. I can give a quick update. Mostly what I was doing, again, was trying to nail down entirely the middle portion of the triple of the typing. And one of the things that was interesting that came out of that was for the subtyping relation, I realized that in the presentation that I gave, I wasn't presenting the evidence as a part of the subtyping. Now we do have evidence in the sense of all the constructors, right? So there's a natural morphism that's being generated. However, treating that morphism, so the question is, under what conditions can we treat that morphism as a process as opposed to just a built-in or primitive constructor? So that opened up some interesting line of discussion. In the most general case, that we end up with something that looks like a dependent type system. So I want to not go down that rabbit hole just yet, but cut it off. And the question is, is there something that's rich that that is better than just the constructors. But that's largely been taking up my thinking process. The other thing I've been thinking about is a different interpretation of the probabilistic, the categories where the trace is built on the probability monad, and there to think of the trace as that's the way to get the faults. So I haven't gone very far down that path, and I'm hoping to report more next Monday. But that's been another place where I've been spending my time. Also, just it's not exactly Casper related, but we now have the Hello World Roland contracts compiling. So those check-ins are available for people to see. And Mike also checked in the grammars for the two different formats for the VM bytecode to go to and to wire. So that part is in, and that means because we're doing it this way, it means it's a lot easier for other folks to do bindings to our virtual machine because we've encoded the format as a BNFC grammar, which means you can generate readers, serializers and deserializers from the grammar for C, C++, JVM, F#, C#, OCaml, Haskell, XML, whatever your favorite flavor is. All of that's available for folks from a single spec. And so that's also checked in, and we can post the links.
What are you? So it sounded like you're serializing something using the grammar, but I didn't really follow what it was for. Initially, I thought you were saying that it was like a kind of contract interface or like a wire protocol, but now I'm not so sure.
It's a wire protocol for the bytecodes. So
we have like RoVM bytecodes.
The RoVM bytecodes, and in this case, it's Rosette VM bytecodes because RoVM is just the abstraction on top of the Rosette VM. The Rosette VM bytecode format is encoded in two different ways. One is a packed byte format for efficiency. And the other is an assembly format for readability. So when you read in the packed bytes, either from store or from the wire, you can display them in assembly style. And likewise, if you want to verify what the assembly does, you can read the assembly and then convert that to packed bytes and execute that against the running VM.
And the grammar just describes how to serialize and deserialize?
Yeah, well, it does more than describe. It actually generates the code for any of those different languages.
So I'm sorry, I don't understand how that works.
So when the compiler,
Mike, you wanna? Okay.
Sure. When the compiler generates a code object, there's the litvec and the codevec, and this is a grammar for the codevec. In that it'll generate internally a bunch of opcodes that are packed 16 bits at a time. And so then when we dump the code object, we'll get a lossless representation of that state. One of them is going to account for every bit. The other one is sorry, why don't I just pull it up?
Just screen share the show.
Great. Yeah. Thanks. So is the Rosette getting transferred into these different languages?
The bytecodes.
The Rosette bytecodes.
the Rosette bytecodes, the format for serializing them and deserializing them is specified as a BNFC grammar. Because it's a BNFC grammar, you can generate a parser for in a pretty printer and so on, directly from the grammar. And also you can generate the LaTeX documentation for it. BNFC is like a gem of a tool, because it allows us to provide a single executable spec for all these different languages. The spec generates the code.
What's ENSC?
BNFC. Here, I'll give you a link.
Yeah. That's one of the many things that I've embarrassingly not done my homework on.
Yeah, no worries.
There it is.
So here's the link.
Okay, so this file here is an H file containing this lovely comment. Here we've got 16 bits. So the halt opcode says the first 8 bits are 0, and then we throw away these 8 bits. You get down to nargs. First 4 bits are 0, the next 4 bits are 0011, and then the next 8 bits are n. And this is how it's used. Okay, so I took this comment and then created these two BNFC things. BNF is Backus-Nauer form. It's a standard way of writing down grammars. So for each line in that comment, it says you read in 8 bits, then you read in a bit 8 arg, so 8 more bits. When you see these 8 bits, you want to read those 8 bits. When we get down to something like this, it says when you see these 6 bits, you read in a 10-bit argument, an 8-bit argument, and an 8-bit argument. So they'll always add up to chunks of 16, but for instance, this last argument gets thrown away. The assembly code, when we get to that same one, where was it?
You're still sharing the H file.
Oh, I'm sorry. I'll have to reshare. So let me go back to this is the binary BNFC. So it says read in 8 bits and then read in another 8-bit argument, in this case that will be thrown away. Without standing, it has a 6-bit argument. The next 10 bits are P, the next 8 bits are N, the last 8 bits are thrown away. So anywhere there's an X, it gets thrown away. So here, read in 6 bits, read a 10-bit argument, an 8-bit argument, and an 8-bit argument. So this is just a literal expression of that comment that was in the H file. And then the assembly format, on the other hand, whenever there's an X, we leave out that argument. So here again, 6 bits, 1 bit, 1 bit, 8 bits, 8 bits, and the last 8 bits we throw away. So this has 1, 2, 3, 4 arguments that show up here. 1, 2, 3, 4. So the assembly code only.
Sorry to interrupt, Mike. Taking a higher level view for a second, if we could maybe just show like the generation of the Haskell or the Java or whatever, so that people can see.
Oh, sure.
Image here.
Hey, did I lose connection? I'm not hearing anything.
No,
I think Mike is just typing.
I'm just typing. Can you see the screen on which I'm typing?
I see your scroll bar.
Yeah. Did you need to put a dot or something or path to BNFC?
Yeah.
Oh, I see. I guess you can do that. No worries.
Library Haskell bin BNFC. All right.
See, so it auto generates the Haskell. There's a similar. If your dash m is Java, generates Java. If your dash m is F#, it generates F#, et cetera, OCaml, et cetera. The point is that now a single spec, we control, we have a single spec that provides bindings for all of those lines, and like down to the code that you should be using for safe serialization from bytecodes and to bytecodes.
So there I just put in one instruction because the first 8 bits are 00000011. The next 8 bits are read as an arbitrary argument. It says there's an instruction sequence. The first instruction is this instr anargs, which is right here, a thing ending 0011. And then the next argument that gets read in is an 8-bit thing, and those are the bits. The reason I'm treating each bit separately is so that I can parse them as tokens. BNFC itself doesn't have bit parsing abilities. So we would have to take this and dump it out as a binary string through the parser. On the other hand, I guess that one didn't have it. The assembly looks a lot more like what you'd expect. Halt. Let's try this one. 1, 2, 3. Oops. What was it? Where's the... Oh, right, outstanding. Okay, so outstanding, can do 0, 0, 0.
We're still looking at there.
So here is an instruction sequence. The first instruction is halt. The second one is an outstanding. These cast things say you can either write a binary bit, which is then interpreted as a 10-bit value, or you can write anyway any number of these smaller things that get cast upward to the appropriate thing. So I can put in a bit and it'll still interpret it as a 10-bit. I can put in a hexadecimal thing with just one nibble, even though it was expecting a byte. Here I put in the whole byte. So yeah, so those two are uploaded, and they're just directly based on that comment. To get a real assembler, though, we'll need a data section for encoding the litvec part of the code object. And so there's more to talk to Greg about how exactly he wants that.
Yeah, we just have to have a literal syntax, which is an efficient literal syntax. But anyway, that's kind of that's another area where we've been making a little bit of progress. Any other updates? Vlad, did we lose you?
No, sorry, I was just muted.
Okay.
No real updates for me other than this kind of stuff that I mentioned about the attribution of faults, and the basically one thing that I didn't mention on the other hand is the role of like a notion of utility that has in this discussion. So basically, we kind of define the utility of the blockchain as the kind of like dollar value of the blockchain to users. And then there's like kind of this principle that like if some fault drops the utility by some amount, then the penalties need to be it can't be it should be like sublinear in that in the utility drop. So basically, like the bigger the utility drop, the bigger the penalties, and we kind of need to define like the utility. And we kind of have this principle right now that we're kind of going with, and it's a little bit interesting. And then the principle is basically that a K factor delay in the finality time is equally bad no matter what scale. So if we delay the finality time from like 1 minute to 10 minutes or from like 1 hour to 10 hours, that loss, those two losses are like the same. And the reasoning there is basically that, the utility of the chain, the utility of finality drops off logarithmically in the amount of time. So basically, finality like every 2 seconds every 2 minutes is worth like quite a bit more than finality every 4 seconds. But the difference between like 2 and 4 is like bigger than the difference between 4 and 6. So there's a kind of like logarithmic scale of the loss in utility due to the unavailability of finality. So basically, with a notion of utility, so basically we have like a few assumptions, like with a notion of utility, and then like some function mapping that to the amount that the coalitions need to be punished, and then we have like this list of coalitions that might have done it, and basically like this is kind of like the information that we have to work with to do this incentivization.
This is really cool, by the way. I think it's really interesting. I'm a little bit, I'm mystified a little bit as to how to make it efficient, but it's a really interesting idea.
Yeah. So, I mean, the nice thing is that we have a decent amount of like breadth of like things that satisfy our bounds. Uh-huh. So like we can do something like relatively simple, say, at least in cases where all of the coalitions that might be faulty are the same size.
I mean, if you have like 1,000 validators, right, and you get less than 2/3, and the number of coalitions is really, really difficult to manage.
Yeah, I hear you. So tomorrow also, we're going to keep working on this, and we're going to have like a couple more people on site. So maybe we'll be able to glean more insight. But basically the plan is to like figure out how to do it like with like some kind of ideal results in the abstract before finding the computationally efficient kind of route. Although like, you know, we have no problem really like finding heuristics that fit it, at least for the finality gadget.
Uh-huh.
So that is kind of, you know, some cause for optimism.
That's cool. That's a really, really neat idea. I'm not sure I understood did you actually describe Vitalik's protocol, or is this it?
I didn't. I could describe it. Let me just do it briefly.
Okay.
Basically, there's two types of messages: prepares and commits. Prepares and commits each have epoch numbers, and they each have hashes. And prepares also point to like the previous hash that 2/3 prepares like happened on. Basically there's like slashing conditions where if you like commit to two inconsistent values, and there's a slashing condition if like the prev hash isn't correct or isn't finalized. Basically, you know, it's like you require 2/3 of prepares before you can make a commit. So it kind of follows the basic outline of a traditional consensus protocol. Only it's like quite simplified by the fact that it's being strapped onto a blockchain rather than having to do a lot of the work itself. It kind of just finalizes the blockchain. And so it gets kind of like free ride on the fact that the blockchain gives people hashes for blocks at particular heights. And that like in a single blockchain, there's like a single block at that height. And so like in a blockchain, a prepare will only be accepted if its hash is the hash of the block in that chain. And so it turns out that like we get a bunch of simplifications to like the reasoning about consensus because it's like because we're kind of free riding on the blockchain for some things. But that also means that like, you know, we inherit the liveness properties of the blockchain, which you know, arguably is partial synchrony, which isn't so bad. But it does require basically a single threaded chain of blocks, which is like, you know, something that is like, this seems kind of highly synchronous. You know, but like weak synchrony, you know, is, I think, a kind of badly named. It should have been called less strong synchrony.
Malnourished synchrony.
Yeah. So, you know, I think by the end of the week we should have like a more kind of like you know, better understanding of like how this stuff that we're doing fits into the kind of traditional game theory literature. But like as a quick summary of what I know so far is basically that in game theory, in like the coalitional like the coordinated game theory, the payoffs are just defined in terms of the strategies, which is to say like, you know, which coalitions form. On the other hand, in our context, we don't have direct access to that. All we have direct access to is the blockchain state, and we have to do this inference of which coalitions form, and that inference isn't perfect, and so that puts a limit on our ability to do the incentivization. And so basically, we need to like kind of add this indirection to different results in game theory and see like how they change, if at all, to see, you know, what kind of results we get to inherit and what results we might have for our particular, you know, for a particular context. And I think it's kind of interesting because I think in algorithmic game theory anyways, the idea that you don't have direct access to strategies is, I mean, it makes a lot of sense.
Yeah.
Well, I mean,
by the way,
sorry, go on.
I think there's a delay. Go ahead. You complete.
Oh, I was going to say that's like pretty much all I have to say for updates.
Okay, cool. No, this is really, really interesting. I sent you a Skype message a while back. Have you ever heard of Moran processes?
No, I mean, I don't know what they are.
Okay, cool. All right, yeah. I was just curious. I just bumped into them a month or so back, and it's an interesting way to relate what you've been doing with the as a possible avenue to relate what you've been doing with the ideal adversary calculation with what I'm doing with the trace. So I just if you already had experience with it, I was interested.
That sounds cool. I would love to talk about that.
Yeah, absolutely. Yeah.
The relationship between the ideal adversary and estimate safety is kind of super interesting, because like right now in my estimate safety proof, I think I'm the proof that a consensus protocol which has estimate safety also has consensus safety. I am relying on assumption that I think is stronger than the assumption I need to rely on if I'm using the ideal adversary. And I think the ideal adversary might be a decent proof method for for showing that estimate safety has consensus safety. But I haven't actually worked that out yet, so I'm kind of speculating.
Interesting, very interesting. Cool. Well, I have to get ready to get on a plane to fly out to New York for this week. So I'm gonna bug out unless there are any like really burning updates.
So is our meeting still on or not?
Yeah. That's why I need to get off now, so I have time to do that.
Yeah, I'm happy to call it quits here.
Cool. All right, guys. See you next week.
Yep. Later. Peace.
Thanks, everyone. Bye.
Ciao.
Bye bye.